Hi there, my name is Robert Dungan and I'm a research microbiologist with the USDA ARS lab here in Kimberly, Idaho. Today I'm going to talk to you about these chambers behind me. They're greenhouse gas emission chambers, and specifically we're monitoring the emission of methane, carbon dioxide, and nitrous oxide. It is a fully automated system. Prior to this we used a manual gas chamber system where we could only go out and collect samples maybe once or twice a week. But with this system, we can measure emissions 24 hours a day, 365 days a year. The chamber system that you see here behind me was purchased from the Queensland University of Technology in Australia. It's manufactured from stainless steel framing, plexiglass. There are lids that close. It operates on a 1-hour cycle. Samples are pulled every 15 minutes. And with that data, we can generate a flux estimate. The advantage is we can account for the emissions much better than the manual system. And our particular interest really is nitrous oxide because it has a global warming potential that's about 300 times that of CO2. There's a couple points that I want to emphasize here. Nitrous oxide is produced by nitrification and denitrification, so that it is essentially driven by microbial activity, and as a result, things like soil moisture, soil temperature, and nitrogen availability regulate the nitrous oxide emissions. The data in the figure here is recent data using the automated chamber system. It's from the fall of 2019 through the present. You notice here that there's a dramatic increase in the nitrous oxide flux throughout this time period, especially for the higher rate of manure application. And there's a few things to point out here, especially that at this point we're in the winter and there are nitrous oxide emissions during the winter, even when soils are frozen. But here in Idaho, it's really sunny a lot. During the warmer days, we'll have thawing events, and during these thawing events, you have a substantial release of nitrous oxide. And you can see here at this inflection point, sometime in probably late January, we have a big increase in the emission of nitrous oxide. Things kind of during this time period here, when we're not irrigating, things tend to slow down a little bit, and then they'll pick up again. During irrigation, which begins at this time of year, we don't have data points here because of a field preparation. What's really interesting is that the cumulative emissions or emissions overall are dramatically higher at this high rate of manure application. And you would expect some type of incremental increase, but you just have this dramatic boost in emissions. So this is certainly an area that needs more research to kind of figure out where this threshold is to prevent having excess emissions from these cropping systems. Going back in time, this is 2016. This is the daily flux rates for nitrous oxide. This is after 4 years of manure application, and the crop was sugar beet. And the data is kind of parsed out into the winter time, early spring, and then later spring through the growing season. And I just don't want to belabor the point, but want to make it clear that there are emissions during the winter, and those emissions during the winter can be equivalent to what you find during the growing season. So it's something we need more research on this. It's something to consider. It's very important. And you'll see once again it's driven by manure application rate. Very high nitrous oxide fluxes with the high rate of manure. When you move to the growing season, you'll see these pulses of nitrous oxide. What's driving this mainly is irrigation events early in the season. What happens is the microcytes in the soil become anaerobic, there's available nitrogen, and the microbes are denitrifying, and so you'll have these major pulses. Kind of a rough estimate would be that maybe 80%, somewhere around there, of the nitrous oxide emissions are occurring during the growing season, during this time of year. So if you could prevent nitrous oxide emissions early in the growing season, at this particular point in time, you could dramatically reduce your overall emissions. And the final slide I have here is normalized data. I think that this is a more important metric than just looking at total emissions. On the left, we have nitrous oxide emissions as a percent of total and applied. What you'll see overall is that The percent of N coming off as percent of total N applied is very low. For fertilizer, it's about 0.25%. And then we have lesser amounts coming off from the manure treatments here. I will say that this data is slightly more skewed with respect to manure because you're really applying more nitrogen with the manure application. A lot of that is tied up in organic matter, and a small fraction of the nitrogen is really available in manure. Moving on to the right, we have the data presented as an emission intensity. That is the amount of nitrous oxide coming off per crop yield. In this particular case, it's metric ton of dry matter. We have the 4 different crops from the beginning of the study here: wheat, potato, barley, sugar beet. You do have an incremental increase under wheat of the emission intensity, with the greatest emission intensity occurring under the high rate of manure. Under potato, things kind of start falling apart here, but you do have a really high emissions intensity under the high application of manure. But this data, as April alluded to a little bit earlier, is skewed because the potato dry weight is much lower at the high manure application rate. And then emission intensities are somewhat similar under barley. Under sugar beet, they're much lower. But I think the point here is that you need to pick a manure application rate that produces a much lower emissions intensity.
In the video, you showed the chambers. Were those chambers installed in every replicating plot?
No, we only have 12 chambers. We pick for the treatments in the study.
What was the temperature delta between inside the testing apparatus and the net ambient conditions?
I have the data. I haven't parsed through it, but we have specific settings for the chambers that will open the chambers if they become too hot. They go above a certain threshold temperature, they will open. At this point in time, for an hour-long sampling period, we haven't had that situation occur.
Based on progress with your field experiments, what are the potential agronomic options for farmers to mitigate nitrous oxide emissions when they use manure as a soil amendment?
The lower the rate of manure, you could help mitigate your nitrous oxide emissions.
The huge differences between emissions with the greatest manure application rate and irrigation events may be related to affinities, Km in parentheses, of enzymes involved in the denitrification process. Is that something you plan to examine?
That's probably delving in a little bit farther than I'm going to go, but it's certainly something to consider.
Do you have a sense for how gas data using continuous measurement compares with manual collection with interpolation?
You know, at this point, I haven't compared the two systems, but from the data I've seen so far, the numbers are pretty darn close.
Not sure specifically what this is referring to, but the fluxes measure all through the year or just during the crop growing season?
When we were using the manual chamber systems, we were mainly doing this during the growing season, but now we run the chamber system all year.